The ultimate objective of a dental impression is producing a negative replica of oral tissues with sub-micron accuracy. The material must capture microscopic surface details while submerged in a highly hostile environment of saliva, blood, and extreme geometric variation. Achieving this level of precision without the material distorting upon removal has been a central engineering struggle in dentistry for decades. The difficulty stems from a physical paradox in the mouth. The impression material must accurately record highly displaceable, wet soft tissues while simultaneously navigating completely rigid hard tissues with locked mechanical undercuts. This diagram outlines the master classification matrix that dictates all material selection. Every impression material is categorized across two absolute axes: its mechanical behavior, whether it is elastic or inelastic, and its setting mechanism, whether it sets via a physical temperature change or an irreversible chemical reaction. Clinical success in capturing oral anatomy is never dictated by the dentist's personal preference. It requires mathematically matching the physical reality of the patient's anatomy to the exact correct quadrant of this chemical matrix. This is the non-elastic quadrant of the matrix. These materials operate under a strict physical limitation. Rigid chemistry cannot navigate undercuts without fracturing. Because of this, their clinical application is restricted exclusively to completely edentulous patients. Impression compound is a physical, reversible material in this rigid quadrant, operating on a thermoplastic phase change. This timeline highlights its narrow thermal window. At 39 degrees Celsius, its glass transition temperature, it begins softening, but only achieves clinical plasticity at its fusion temperature of 43.5 degrees Celsius. Because the compound has exceptionally low thermal conductivity, the outer layers soften rapidly while the core remains rigid. It requires heavy mechanical kneading to achieve uniform plasticity. This highly viscous consistency results in a mucocompressive material that physically displaces soft tissue under pressure. Moving down the y-axis brings us to zinc oxide eugenol, or ZOE. This represents the chemical, irreversible side of the rigid quadrant. Rather than relying on heat, ZOE utilizes an acid-base chelation reaction. The zinc oxide acts as the base and reacts with the eugenol, which functions as a weak acid. Together, they bind into a fixed, solid zinc eugenolate matrix. Unlike the heavy, mucocompressive compound, ZOE possesses extremely high flow. It registers surface detail accurately without displacing the tissues, making it a highly effective chemical wash to layer over a rigid thermoplastic primary impression. Dentate patients with undercuts require the elastic quadrant of the matrix. The foundational elastic materials are aqueous hydrocolloids. A colloid consists of specific particles suspended completely throughout a water dispersion phase. To function clinically, these materials must undergo a physical phase transition, converting from a flowable liquid sol state into a stable cross-linked semi-solid gel state. Agar is the reversible hydrocolloid. It is intensely hydrophilic, and its sol-gel phase transition is driven entirely by temperature manipulation. This dual line graph illustrates hysteresis in agar, an extreme temperature lag in physical properties. It requires a 100 degrees Celsius liquefaction point to melt into a sol, but the temperature must plummet to 37 degrees Celsius to achieve its gelation point. Occupying the chemical, irreversible side of the elastic quadrant is alginate, the most widely utilized hydrocolloid in dentistry. Alginate bypasses temperature entirely through a rapid cross-linking chemical reaction. Soluble sodium alginate reacts directly with a calcium sulfate reactor to precipitate an insoluble calcium alginate gel. Left alone, this reaction occurs too rapidly for clinical use. Engineers add trisodium phosphate as a chemical retarder. The calcium sulfate will preferentially react with the retarder first, intentionally delaying the primary cross-linking reaction to guarantee the dentist adequate working time. Both agar and alginate share a fatal thermodynamic flaw. Because their matrix is primarily water, they are incredibly volatile. Left in open air, they exude fluid and physically shrink, a process called syneresis. Immersed in water, they rapidly absorb moisture and swell outward, known as imbibition. Hydrocolloids are perpetually fighting thermodynamics. To prevent severe dimensional distortion, the clinical protocol mandates that these impressions be poured with gypsum immediately after removal. To solve the severe instability of hydrocolloids, material science developed non-aqueous elastomers. Instead of relying on a water dispersion phase, these materials utilize robust synthetic polymerization reactions. The first elastomers were polysulfides. They achieve massive tear strength by oxidizing terminal mercaptan groups with lead dioxide. However, this specific chain-lengthening reaction produces water as a chemical byproduct. Condensation silicones attempt a different chemistry. They cross-link hydroxyl-terminated polymers, but this specific reaction releases ethyl alcohol as a byproduct. This animation demonstrates the byproduct problem. As the shed water and ethyl alcohol molecules inevitably evaporate from the set material over time, the overall impression experiences severe dimensional shrinkage. The breakthrough was addition silicones, or PVS. Vinyl-terminated siloxanes react directly with silane hydrogens, catalyzed by a platinum salt. Because molecules add together without shedding byproducts, PVS maintains exact volume, achieving elite dimensional stability. The occasional release of hydrogen gas is neutralized by adding palladium. Polyethers represent the final evolution in this category. They utilize a ring-opening polymerization via an aromatic sulfonate. This creates an elastomer that is inherently hydrophilic and highly rigid, making it ideal for the extreme mechanical demands of implant dentistry. By completely eliminating volatile chemical byproducts, PVS and polyethers achieved a level of dimensional stability that severed the need for immediate pouring. Impressions could now maintain accurate spatial data for days, completely restructuring how dental clinics interface with commercial laboratories. This radar chart maps the reality of these chemical categories, revealing strict clinical trade-offs. We secure elite dimensional stability and tear strength with PVS and polyethers, but we sacrifice the intense natural hydrophilicity and cost-effectiveness inherent to Agar and Alginate. Conversely, we gain ultra-precise, flowable tissue capture with a rigid material like Zoe, but we completely surrender the mechanical ability to navigate hard tissue undercuts without fracturing. A mathematically perfect, universal impression material does not exist. The physical properties required to capture displaceable, wet, soft tissues are inherently contradictory to the properties required to navigate locked, dry enamel. True clinical mastery is not a search for one flawless material. It is the ability to accurately predict the chemical mechanics of a specific matrix and perfectly deploy it against the unique physical geometry of the patient in the chair.